Hey there, Calc 2 folks, back here with another video in our study of Chapter 12 material. Here we're looking at really different ways to describe position and location and motion, in a sense, in coordinate spaces. And here what we're going to do in this bit of notes is introduce ourselves to an alternative way of describing what we're familiar with as the XY coordinate system. Right? We, by now in our calculus and algebraic study, should be quite familiar with the XY coordinate system. And that is a coordinate system where we represent location in our coordinate space by the XY coordinate given by in what we might consider this example x1 comma y1, where x represents some sort of displacement that happens along the horizontal axis, and y equal to y1 describes some sort of displacement that happens along the vertical axis. Where when those two descriptions of displacement come together as this coordinate, right, they highlight a location in space that is illustrating these two descriptions of displacement simultaneously. Right? Where, we are again very familiar with the XY coordinate and how to go about describing position and location and even maybe the idea of motion in this two-dimensional space. Here, right? We're very familiar with the XY coordinate plane, right? What we move into now is we take note that in addition to using the XY coordinate to talk about location in two-dimensional space, we can also use what's known as a polar coordinate, right? A polar coordinate, right, denoted as what we would say is this coordinate location r comma theta. It is also a two-parameter description of location. Right? Where specifically we might say we have r comma theta equal to r1 comma theta 1 as our description of a polar coordinate. Where what do I mean by this parametric description of location given by r comma theta? Well, this is where if we think about having this location in space, we think about this location in this XY coordinate system or this two-dimensional system being highlighted right here at this location, which will now denote as the polar coordinate r comma theta equal to r1 comma theta 1. Right? What we mean by that description of location is if we go about drawing what we call a radial arm from the center of this origin, or I should say here from the center or the origin of this two-dimensional space through this location. If we imagined this line coming from the origin and passing through this location at what we would call r1 comma theta 1, the value of r equal to r1 would actually describe the distance along that radial arm from the origin to this location, right? R1 is just the description of distance from the origin to the location that we're describing with our polar coordinate. Whereas the value of theta equal to theta 1, it's what we think of as being an angle measurement. An angle measurement that forms between that radial arm passing through the origin and this location and the positive x-axis, right? There's going to be an angle that forms here. That angle measurement is what we call theta equal to theta 1, all right? When we put together this description of theta equal to theta 1 and r equal to r1, we get this description of location in our coordinate space, described by the polar coordinate r comma theta equal to r1 comma theta 1. Right? If we look at a particular example here. Oh, before we get into that example, we would take note here that that location r comma theta equal to r1 comma theta 1 actually be described by an infinite number of different polar descriptions, right? All pending some value of r, where r can be any real number, and angle measurement theta, right, which also can be any real angle measurement. All right, what do I mean by that? Well, this description, right, in terms of location in this two-dimensional space, if described using the polar coordinate r comma theta, that description in the polar context actually can happen with an infinite number of different descriptions, right? Which vary, right, pending these values of r and theta, where r again and theta again can be any real number in their description, right? That's a little different than describing that location in the xy coordinate system. If I was to go back and describe this location with respect to x and y, there is only one x and only one y value that this location is occurring at. In terms of polar coordinates, though, there's actually an infinite number of different descriptions that we could develop for this description given by r1 comma theta 1. All right, what do I mean by that? Well, there's an infinite number of different angles that describe this angle being formed here, right? Theta equal to theta 1 in this illustration actually only illustrates one of those angles, the smallest angle, where we could consider the angle forming where we actually go one full revolution around the origin. If we were to go one full revolution around the origin, we could actually describe this angle measurement as an angle that's greater than 2 pi units in radian measurements, right? Or we could go 2 times around it and describe it as being greater than 4 pi radian units, right? And so forth, right? When we think about that angle measurement at r1 comma theta 1, we could think of it at being at the location r1 comma theta 1 plus 2 pi k, where k, we're going to note, is just any integer value. And k describes the number of revolutions we're going around the origin before stopping at this radial arm. And we could make no revolutions, where theta equal to theta 1 would be the smallest angle measurement, just theta 1, or we could make more than one revolution, right? Or one or more revolutions, where we would add on a 2 pi to that measurement each and every revolution. And this could happen in both the positive direction, or in the case of k being negative, that would be back in the negative direction. Now, in addition to that, r comma theta could actually be described with a negative value for r here. Right? Instead of thinking of r1 being, in a sense, positive in its distance, it could be thought of as being negative in its distance. Now, you'll notice it would be considered negative in its distance if we were at theta 1, but half a revolution away in that description. Half a revolution away being in the opposite direction of what we consider currently as our angle measurement for theta 1. If I was in the opposite direction, in this direction perhaps as I'm indicating here, right, compared to this angle measurement for theta 1, the direction given back here would actually be in the negative direction with relative to the values or the description of r, right? So what we can say is we can have actually negative values of r if we were to be considered at some angle measurement that was half a revolution away from what would be a current angle measurement of theta 1. And not only could we be half an angle measurement away, we could be any full revolution beyond that half measurement highlighted by 2 pi k, right? Where either of these descriptions would be appropriate in their description of location, right, given by r1 comma theta 1, right? And because k can be any integer, there's an infinite number of these different descriptions. If we were to look at now at a specific case, we might consider the polar location described here by r comma theta equal to 3 comma 2 pi over 3. That would describe this location right here in space. This location right in here in space is 3 units from the origin, and you'll notice with the scale of the x and y axes that this would fall right at the measurement of 3 units away from the origin, right? And it is located on a radial arm that, if we thought about this line passing from the origin through this point, that radial arm would form an angle measurement with the positive x-axis here that would measure 2 pi over 3 radians in degree, or in measurement, in angle measurement. All right, 2 pi over 3 radians. All right, now that does describe this location in this two-dimensional space. As we've highlighted, though, this location can actually be described using, in the polar context, I should say, with respect to an infinite number of different descriptions. In addition to this description, we can use the formulas we see here above, right, to come up with the other infinite number of descriptions that would be possible to describe this polar location. Right? If we were to put those values of r and theta into those formulas, right, this coordinate r comma theta equal to 3 comma 2 pi over 3 could also be described by either this description of r comma theta or this description of r comma theta, where you'll notice this first description considers r still being positive 3, but being at some number of revolutions around the origin before considering this location at 2 pi over 3. Or in the second description here, considers the case where r is negative 3, where we're at a radial arm measurement of 5 pi over 3, and considering the different number of revolutions we could be making around the origin to come to this location. All right, notice 5 pi over 3 is actually the angle measurement forming here down into quadrant 4, where if we think about this radial arm forming this angle measurement 5 pi over 3, right, in this illustration, we would actually be back in the negative direction 3 units to describe this location here. All right, that's what's being described with this description here where r is negative 3 in value. Negative 3 with respect to r doesn't describe a negative in terms of value, but describes a negative value in terms of direction. Right? This is 3 units in the negative direction along some number line whose angle measurement with the positive x-axis forms 5 pi over 3 units. 5 pi over 3 radians in measurement. All right? And you can be any, cycle around the origin from that measurement, which would be 2 pi times k, k again being any integer. And if k was 0, you would see the 3 comma 2 pi over 3 description, or maybe negative 3 comma 5 pi over 3 description. But if you were to make k, for instance, the value of 1, you would just add 2 pi to each of those angle measurements. And we take note of that down below here. All right? Note when k equals 0, r comma theta is either described by this measurement, or this location, or this location. But when k is 1, we end up getting these descriptions of that location below. Right? Where here, for this one location described by 3 comma 2 pi over 3, we see these 3 other descriptions of location. One for the negative direction, right, of r being negative 3 units at an angle measurement of 5 pi over 3, and then the cases where we consider being 1 revolution in either the positive or negative direction from these 2 revolutions, right, or angle measurements, right? That would be given by 8 pi over 3 or 11 pi over 3. Now, the next situation we want to consider is how do we convert between these two descriptions of location that we have? How do we convert between the rectangular description for location given by the xy coordinate and the polar description of location given by the coordinate r comma theta, right? And what we rely on is a little bit of trigonometry, right? Applying trigonometry to this above illustration, where we can note we could form a right triangle in this illustration whose hypotenuse is this measurement given, well, falls along this radial arm whose measurement would correspond to the value of r sub 1. X's value would correspond to the adjacent side of this right triangle, and y1 would correspond to the what we would say is the opposite side of this right triangle, where the angle measurement theta would describe this angle measurement here for one of the angles that is not the right angle in this triangle, right? For the angle measurement here between our adjacent side and the hypotenuse. Right? And using just a little right triangle trig, you could say the cosine of theta is going to be your adjacent side over your hypotenuse. Well, that's going to be x over r. So that means x is equal to r cosine theta. And that is what we see described below here. Right? X is equal to r cosine theta in this relationship. If theta is this angle measurement here, and y is this opposite side measurement, then the sine of theta would be y over r1, or y over r. So that means y would be equal to r sine theta, and that is what we see in the description down below here. Y is equal to r sine theta. And then if we were to apply a little Pythagorean theorem, we would be able to develop this relationship between r and the values of x and y, right? From Pythagorean theorem with a right triangle composed into this illustration here, you would note that r squared, the hypotenuse, would be equal to x squared, the adjacent side squared, plus y squared, the opposite side squared. And you'd be able to apply a little, right triangle trigonometry and the understanding of the tangent to come up with a description of theta in terms of y and x, or x and y. That being the tangent inverse is y over x in value. Because if we think again as this being the angle measurement theta that falls between the hypotenuse and the adjacent side, the tangent of theta would be opposite y over adjacent x. So if the tangent of theta equals y over x, theta then must be the tangent inverse of y over x in value, right? And we can prepare these four equations to describe the relationship between the rectangular coordinate at x comma y and the corresponding polar description of that location given by r comma theta. Right? If we were to look at a example here, we might note when r comma theta equals this location 3 comma 2 pi over 3 that we saw in the previous example, the corresponding rectangular coordinate given by x comma y, right, or would be such that x would be equal to 3 times the cosine of 2 pi over 3, r being the value of 3, theta being 2 pi over 3. We would just plug r and theta into this formula up here for x and find, since the cosine of 2 pi over 3 is negative 1/2, 3 times negative 1/2 in value, which is negative 3/2 for x. And y would come from the formula r sine theta. 3 times the sine of 2 pi over 3. And the sine of 2 pi over 3, well, that's what? Square root of 3 over 2. So y's value would come from just 3 times the square root of 3 over 2, which would be 3 root 3 over 2. All right? And that description given by that polar coordinate r comma theta equal to 3 comma 2 pi over 3 would actually correspond to the rectangular coordinate negative 3 halves comma 3 root 3 over 2. And if we go back to our illustration here, right, notice the x coordinate is at negative 3 halves or negative 1.5, which is right down here. And the y location would be at what we would say is that irrational value, 3 root 3 divided by 2, which is right about here on our number line for y. All right? Now, if we were to convert a rectangular into a polar, we might consider the rectangular coordinate 2 comma negative 2. All right? If we're considering that as our rectangular coordinate, right, using the Pythagorean theorem, r squared would be equal to x squared plus y squared, which would be 2 squared plus negative 2 squared, or just 8 in value, implying the measurement for r we could be using would be either plus or minus 2 root 2, or plus or minus the root of 8. Right? Where the plus or minus would come up with whether or not we were using, well, if we were considering that distance to be in the positive or negative direction along our radial arm. As for orientating ourselves in terms of an angle measurement, we would note theta would be equal to the tangent inverse of negative 2 over 2, which equals the tangent inverse of negative 1. And if we go back to our right triangle trigonometry, the tangent inverse of negative 1 corresponds to the angle measurement negative pi over 4. So we could describe this angle, or sorry, this location using the polar coordinate, right? 2 root 2 comma negative pi over 4 plus 2 pi k. Or, if we consider the negative direction, right, we could add a pi over 4 to negative pi over 4, and that would put us in, well, add a pi to negative pi over 4, and that would put us in the angle measurement 3 pi over 4, and cause this distance to fall in the negative direction there, folks. Right? Again, where in either of these two descriptions, k can be any integer value. All right? So, folks, to begin with here, this is just a little, well, the beginnings of what we think of as being the polar coordinate system, and describing location in this two-dimensional space that we're familiar with describing in the rectangular coordinate system, now with this idea of a polar coordinate. A polar coordinate describing location by describing some distance from the origin and some angle measurement falling, well, between a radial arm passing through this location and the positive x-axis. All right? What we have to come back to, folks, there's a little bit more left in this study here, and that has to deal with what we call polar equations, or what we're going to find are we're going to encounter known as polar functions, and their graphs which produce some polar curves. So we are going to come back and look at that next, folks. So I'll be right back in the second part of this video to show you those ideas. All right, Calc 2 folks, back here with the second half of this lecture, introducing the polar coordinate system, where I want to spend a little time on looking at what we call or defining what we call the polar function, and what are known as polar curves, folks. So One thing we note is in the polar coordinate system, relationships exist between r and theta, right? Just like in the xy coordinate system, we have relationships that exist between the variables x and y. In the polar coordinate system, we do have relationships that exist between the variables r and theta. And if these relationships are functional, such that when we think about r, it might depend upon what angle theta we happen to be at. This relationship can be expressed using function notation given by this statement here, r equals f of theta, right? Which denotes a polar function, we say, right? Here we have r, the dependent value, in a functional relationship with the independent value being the value of theta. Here we have the idea of that idea of a function, which means we have a relationship where for each value of theta, there corresponds just one dependent value of r. There corresponds just one radius measurement r, right? No matter what angle measurement we happen to be at in the relationship, right, theta, there'll always just correspond one value of r, indicating this functional relationship, right? Now, we can go further and note the graph of a polar function or relationship, a polar relationship in R2, illustrates every single solution to that relationship and is known as a polar curve, right? When we think about the graph of something like a polar function, right, this value r equal to f of theta, that graph is going to highlight every single value of r and theta that makes this relationship true. And that graph is known as a polar curve. Right? If we consider a case here, right, we might consider the polar relationship where r equals 2 plus the cosine theta. And what you will notice here is we do have a functional relationship between the values of r and theta. For each value of theta, there is going to correspond just one value of r in this relationship. And we could express that explicitly in this function notation, with this function notation replacing our value of r with the value f of theta, right? R is equal to f of theta in one of these polar functions. And as we see in this case, r equal to f of theta is the case where f of theta is equal to 2 plus the cosine theta, right? And for every single angle measurement theta, when we take the cosine of that angle and add 2 to that result, we will have a functional relationship with r, right? We will have an output, a dependent value, where there will be just one dependent value for any given independent value. Now, as with the beginnings of our exploration of just functional relationships back in algebra, right, one way we can start to explore this relationship would be looking at a table of values, right? And in a functional relationship, your independent variable theta, right, might make up your first column, so we can see all these angle measurements here for theta. And you could expect angle measurements from 0 all the way up to 2 pi, right? Where here for r equal to f of theta, we do see values for r that cycle anywhere from 3 down to the value of 1 and then back up to the value of 3, where we do note that there is a bit of cyclic behavior happening in this relationship that occurs for every cycle of the cosine function. For every cycle from 0 to 2 pi, the cycle repeats itself, right? We have the values of r repeat themselves. Now, that still is functional in behavior, folks. For each of these independent values of x, for any given angle measurement x, they'll always just correspond one value over here for r, which makes it a functional relationship, or in this case, a polar function. All right? Note, again, this table does cycle over values of theta in this interval from 0 up to 2 pi, right? We're starting at 2 pi. The cycle repeats itself for these values of r, which also can be seen in the polar curve for this relationship, right? Where the polar curve is going to illustrate every single solution to the polar function, is going to illustrate all infinite solutions to this polar function, right? And the graph of this polar function is illustrated as follows, where what you will want to recall that in this illustration, these values of r that we see in the table are going to be distances from the origin, and these angle measurements of theta are going to represent an angle measurement that forms between the radial arm and the positive x-axis, where we happen to find each of these corresponding solutions. And if we interpret that information, those values of r and theta appropriately, this is the graph of that polar curve, right? This would give us the corresponding graph of this polar curve, and in fact, we might copy this down here just so we can compare the two side by side a little bit more easily, if I can. It's really going to be a bugger, huh? So let's put that right there. And that's not too far out of view. We can see that there, right? As we cycle around this polar curve, right? But what we can see here is if we started an angle measurement of theta, that would put us right on top of the positive x-axis, where we will see that we are a distance of r units away. We are a distance of 3 units away. When we cycle up to an angle measurement of theta equal to pi over 4, that's on this radial arm right here, we will be a distance of 2 plus the square root of 2 divided by 2 units away. So that's somewhere between 2 and 3 units away, right? And that puts us right there, right, at that particular distance. When we cycle over to pi over 2, which is falling along the positive y-axis, we are exactly 2 units away, which puts us right there. And as we cycle around to 3 pi over 4 units away, that puts us on this radial arm at a distance of 2 minus the square root of 2 units away, which would put us at a distance right there from the origin. And at the value of pi, we do see the value of r equal to 1. That puts us on the negative portion of the x-axis, and we are going to be at a distance of 1 unit away from the origin. Right? As we cycle around to 5 pi over 4, we do see that we return to 2 minus root 2 over 2 distant units away from the origin. We're at 3 pi over 4. Sorry, that's going to be 3 pi over 2. In the negative direction along the y-axis, we will be at 2 units away. So that puts us at negative 2 on the y-axis. And as I cycle all the way around towards the end of the table here, at 7 pi over 4 will put me on this radial arm at, again, a distance of 2 plus root 2 over 2 units away from the origin. Where when I complete the cycle at 2 pi, I'm back on the positive x-axis at a distance of 3 units away. Where if I just continue cycling angle measurements from 2 pi up to 4 pi and 4 pi up to 6 pi and 6 pi up to the value of 8 pi, I'm just going to continue cycling around this polar curve in the counterclockwise direction here, right? If I was to consider those angles forming in the negative direction, I'd be cycling around this polar curve in the negative direction, right? And what this polar curve does illustrate is that cyclic behavior between angle measurements of theta and r, where, again, r is going to be interpreted as this distance away from the origin, where each and every one of these points happens to be falling along some radial arm whose angle measurement with the positive x-axis measures theta units in degree or in radians. Here's how we're interpreting that. All right? Now, what does help us in our interpretation here, and as you put together these polar curves, you may actually be going back and at times interpreting the rectangular relationship, right, for the polar function described in our polar curve, right? What might help us to understand the shape of this curve, even though we only looked at a few finite locations here in the table, right? How we can kind of fill in the gaps between these angle measurements of theta is to consider what the graph might look like down here for the corresponding rectangular relationship. If we were to consider in the rectangular context letting y equal r and x equal to theta, where y then is just going to describe some displacement away from the x-axis relative to the horizontal axis here, and x is just going to be equal to theta, describing some location along the horizontal axis, right? The corresponding curve given by 2 plus the cosine x would be this classic cosine wave. This classic cosine wave that is shifted up 2 units in space, which produces this cosine wave here, where, again, this vertical height is being described by r, and that angle measurement is really just this location along the x-axis, where we can see if we're at a angle measurement of 0, we are 3 units away. At pi, though, we're 1 unit away. And then that cycle repeats again at 2 pi. At the value of pi over 2, we are 2 units away, and the same goes with 3 pi over 2. And at those values of pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, we're either 2 plus root 2 over 2 units away or 2 minus root 2 over 2 units away, these locations down here. Where these vertical distances we see in this graph correspond to these radial distances from the origin, right? This distance from the origin from 0 to 3, seen here in this polar curve, is the exact same distance that we see vertically here at 0 and 2 pi. Up to the graph, that is 3 units up to that location. It's 3 units up to that one. At pi, we were 1 unit away from the origin, right? This highlights a height of 1, and we see that in the graph. We are 1 unit away. So how the curve behaves as it cycles around this has its distances illustrated in this graph of the function 2 plus cosine x in the rectangular context. And what we do see is that the furthest we are away from the origin is 3, and then that decreases to 1 as our angles cycle from 0 to 3 pi. We're at the value of pi over 2, we are 2 units away, and at these other measurements, 2 plus root 2 over 2 and 2 minus root 2 over units away, respectively. And that behavior, as we see here illustrated in the cosine wave here, is symmetrical in its distances. So we see that element of symmetry occurring with respect to the origin in this system, right? Our distance away, starting at 3 and decreasing as we cycle around to pi, at a closest distance of 1 unit away occurring at pi, then grows from 1 unit away back to 3 units away in a very symmetrical description relative to what we saw in the upper half of this polar curve. Right? So when working with polar curves, folks, and we're going to see a couple more examples as we move forward into the next section where we're going to have to graph these out, what might help you at times in understanding what your polar curve might look like is actually graphing its corresponding rectangular interpretation, right? Where we're pretty used to graphing something like 2 plus cosine x in the rectangular system, and with this understanding in place and knowing that x is now going to describe our angle measurements and this vertical distance of y is going to describe our radius, we can interpret the picture here, the illustration in the rectangular context, to help us derive this illustration we see here in the polar context. All right. So, folks, that is the end of our introduction to the polar coordinate system. We want to know how to plot points within that system, which, all right, going back over, we can consider each and every one of these pairs of solutions in our table here are just coordinates in the system that we have to know how to plot, right? They do have a relationship to the x and y values seen in those four equations that develop from right triangle trigonometry. And just like in the rectangular system, we do see relationships between r and theta in the polar coordinate system, where if that relationship is functional, such that for each value of r, there's one, or for each value of theta, there's just one corresponding value of r, we have what we call a functional relationship. And we can express that in general terms as this polar function r equal to f of theta, which does make use of this function notation. And the graphs of these polar equations, these are just polar curves, right? And to graph a polar curve, you want to keep in mind how r and theta are interpreted, which gives us the respective illustrations of a polar curve. To help us interpret that polar curve in the polar context, we might consider what it looks like in the rectangular context. All right? So, folks, that is, again, our introduction to the study of the polar coordinate system. What we're going to come back to is a little bit of calculus that happens in this system. We are going to be looking at slope of the line tangent to a polar curve, right? We're going to come back and look at an idea that might deal with how do I find the slope of the line tangent to this polar curve right here at this coordinate? Or we might consider finding the length of this curve. We're going to look at arc length for polar curves. And or we might look at what's the area trapped within this polar curve, right? Or what's the area trapped in half this polar curve, or just in this one quadrant of this polar curve. Right? We'll be able to develop methods for calculating that trapped area in a polar curve. So, folks, that is what's going to come in the next section here of notes that I'm going to present to you in a video lecture, and I'll be back shortly with that video, I hope. So, I'll see you all then.